Okay, so welcome everybody to the Geometry and Model Theory seminar. Today we have the pleasure to have Neer Bhardwaj from Urbana-Champaign, and he's going to talk about the Pila-Wilkie theorem.
Thank you, Tamara, for the introduction and the organizers for invited me to give a talk. I'll talk about my work with Lau, where we sort of provide a simplification of part of the proof of the Pila-Wilkie theorem. And actually, I plan to give some of a fairly detailed sketch of our work. And and apologies to people who have sort of seen a version of this talk before. There will be significant overlap if you have been in the audience before, but there are some changes. So hopefully it will be worth your while. Okay, so let's start. I like to start this talk by a problem that I was introduced to by through a paper of Wilkie's. So this appeared in Putnam 1971, and nobody could solve it in that exam. And so let alpha be a positive or a non-negative real number, such that 1 to the power alpha, 2 to the power alpha, 3 to the power alpha are all integers. The problem was to show that alpha must also be an integer, right? So let me phrase it this way. So, for example, let f be the function such that x goes to x power alpha, where alpha is a real number. And if we have that f maps the natural numbers to natural numbers, then alpha itself must also be a natural number. And so the sort of intuition that appeals to everyone here is that since if alpha is not irrational, this function is not very algebraic and so on, and it's in fact transcendental. I mean, I won't define what I mean by transcendental right now, but perhaps soon enough. And so this function is not algebraic and has a transcendental quality to it and should not contain too many rational points. By rational points, I mean points where x and the input and the output are both rational points as well. So x and x to the power alpha are both rational. So that should not happen too many times or at all, right? And so this is sort of the guiding principle with these fine-tuned results here that we'll see, and the Pila-Wilkie theorem itself as well. In fact, for this problem, we only need to assume that we have that 2 to the power alpha, 3 to the power alpha, or 5 to the power alpha are all integers. Or pick any 3 other primes. This is a theorem of Siegel and so on, but that's for another day perhaps. And so okay, but let me now start building up towards the Pila-Wilkie theorem. Yes, so we want to show that transcendental sets contain few rational points. What I mean by transcendental, I'll come to that later. But what I mean by few rational points, let me get to that now. So some notation. And so to every rational number a over b, where a and b are co-prime, I want to assign it a height, so that the height of a over b is the maximum of the heights is equal to the maximum of the absolute values of a and b. It's a natural number. And also I want to assign a height to a tuple of rational numbers. And so height of a tuple is just the maximum of the height of each of the coordinates, and so on. And so I want to look at rational points on some subsets of Rn, by which I mean the intersection of x with q to the power n. And so I define this set xq. And then I sort of want to measure scarcity or some sort of density. And so I define this set, which is finite, xqt, which is a set of rational tuples on x of height at most t. And so this is of course finite, and so I set nxt to be the cardinality of the set xqt. And so our focus would be on this set nxt for certain x. And so to fix notation, n would always be a natural number that is not 0, small n, and capital T would always be a real number which is at least 1. And so, as I said, our aim would be to look at this number nxt and really we'll look at some upper bounds on this number. And to be precise, we'll look at big O to the power t to the power epsilon sort of bounds or subpolynomial bounds in T on this number nxt. So that we suggest that really can't have too many points. Okay, but let us get started with our first result for the day. this is due to Pila now some more than 30 years ago. And so let X be the graph of a transcendental analytic function. Again, I'm putting off defining transcendental now, for now. And so if X is the graph of a transcendental analytic function, for every epsilon, there is a C such that the number of rational tuples on X of height at most T is bounded above by C into T to the power epsilon. And so here, of course, the major point is that this C works for all T as set T to be bigger than or equal to 1, right? And so this is the sort of the quality of the bound we'll be looking for throughout. So this displayed equation would sort of look sort of the same or very similar to the displayed equation here in all the results we'll see today. And so again, to set more notation, epsilon C for me would be always real numbers which are positive. Okay, so this was so X was a graph of a function, so sort of one-dimensional graph of univariate functions, so sort of a one-dimensional object really. But what about higher dimension? So okay, let's look at the next dimension, dimension 2 objects. So let's look at this set. All right, so this set sort of has this boundary that is not algebraic. One of its boundaries is part of the graph y equal to ex, and but so it sort of has a transcendental element to it, this set X. But you see, I mean, for example, if you look at this line X equal to 0.5 or y equal to 2, one of the coordinates is rational, and you see you have a lot of other rational points on these straight lines, and so we can't hope to get really in this case, even though X is not X has some transcendental quality to itself, we can't hope to get the quality of the bound we had on the previous page. All right, and so it's really hopeless, but we can sort of remove all the obvious things that are going to cause us problems, right? If you remove every semi-algebraic curve inside X, or all infinite connected semi-algebraic curves inside X, or all infinite connected semi-algebraic subsets of X, then I mean, these are the obvious things that are going to cause us trouble. If you then perhaps maybe there's a chance, and it turns out it is okay in a lot of situations. It is the right setting to work with, and so now let me set more notation. So the transcendental part of X would be X with all these connected infinite connected curves taken out of X, right? Connected semi-algebraic curves taken out of X. And so then there was a result again by Pila. So if X is now a dimension 2 set, which is compact and subanalytic, and so a subanalytic set, you can think about taking analytic sets, closing them under Boolean combinations, and those sets are called semi-analytic sets. And then sort of if you close them under projections, you can call them subanalytic, and you can think about this like that. And so if X is compact subanalytic and of dimension 2, and it can be inside any Euclidean space of any dimension, then you get the same quality of bound for the transcendental part of X. You have to remove these obvious obstructions. And so the number of rational tuples of height at most T on the transcendental part of X is bounded above by C into T to the power epsilon. And again, of course, the C works for all T. All right. But if you go back to the example on the previous page and look at the transcendental part of this set, right? I mean, really every point here in this set lies on a semi-algebraic curve, and so really the transcendental part of X is trivial, and hence this statement makes a trivial assertion, right? But now let's look at an example for which the transcendental part of X is somewhat more involved. Okay, so let's consider X to be the set of tuples X, Y, Z in R3, such that Z is equal to X to the power Y. All right, and so I bound the values for X and Y. So this is like a bounded set. And so we see that for curves of the form Z equal to X to the power Q, where Q is a rational number, that's semi-algebraic, and this is part of this set, right? And in fact, that is exactly the algebraic part of this set X. And so the transcendental part is given by this. And so in particular, you see this transcendental part has infinitely many connected components, and is not subanalytic because bounded subanalytic sets have only finitely many connected components. And so people who see where this is going, right? I'm going to soon consider X to be definable in homonomial expansion of the real field, and such X have only finitely many connected components. So this sort of shows us that even though X might belong to a special class of sets, the transcendental part of X may not be in that special class of sets. Or in other words, if X is definable, the transcendental part of X may not be definable in a very emphatic way, in a certain sense. Also, the fact in the displaced equation it's mentioned in many places, but we were not able to find sort of reference for it. So in our note, we actually provide a proof of this fact as well. Okay, and now, so for the first result, we looked at X, which was the graph of an analytic function. Then we looked at X, which was of dimension 2 and was compact subanalytic. But if you consider the class of all compact semantic sets, these sets are definable in a first order structure, which is O-minimum. And in fact, O-minimality turns out to be one of the natural settings for generalization here. And so, in fact, now if you have X to be a set that is quote unquote definable in an O-minimal expansion of a real field, then you have the same sort of result that we had for compact semantic sets of dimension 2. In that, the number of rational tuples in the transcendental part of X is bounded above by C into T power epsilon, where C works for all T. And so in particular, all compact semantic sets of any dimension are included in this setting. But there is much more. I mean, there are sets which are nowhere analytic and definable in an O-minimal expansion of the real field, and so on. So this is significant generalization in more than one direction. All right, and so I want to discuss part of the proof of this theorem. But okay, I have this slide where I define an O-minimal expansion of the real field, but looking at the audience is perhaps not necessary. But perhaps people who have never seen such a thing, let me just say a few words. I mean, so we are looking at the class of sets, which I have already called definable in an O-minimal expansion of the real field. You can know that if X is such a set and is also one-dimensional, it is also a subset of the field R and definable, then it's just a finite union of points and intervals. So in fact, in particular, has only finitely many connected components, and this is a feature that is shared in this setting by even higher dimensional sets. And you have the cell decomposition, which is the major thing we use, and the only thing we use for our simplification, and which I also sort of push under the rug when I discuss the sketch. But anyway, I'm going to skip going to details here. Any questions for now? All right. Now let me focus on the Pila-Wilkie theorem. All right. Okay. So in what follows, I now fix an O-minimal expansion of the real field, and I call it R tilde. I fix this R tilde. And when I say definable, I mean definable with respect to this field R tilde. Fixed for now. Okay. And we follow in our note Pila and Wilkie's proof, which it relies on two intermediate results. Okay, some things about those results. So one of the results is sort of an interpolation result, which goes back to techniques of Bomberry and Pila, and perhaps even older than 1991 paper of Pila's. And then there's a second result, which is really O-minimal version of the Yomden-Gromov algebraic lemma. And so now the version of our paper that's available on the internet. We've sort of made changes to it, and now we do the Yomden-Gromov O-minimal business following Binyamini and Dmitry Novikov's simplification, and we don't do it for cellular maps. We do it for the usual thing. But okay, maybe we'll release it soon. But that is also something I wanted to point out. So hopefully, it's now people can read our note and will find it very simple to understand the whole proof. But anyway, but for this talk, I use this as a black box. So, and I use following result where I combine these two ingredients and I just use it as it is. All right. So suppose X is inside this compact box, -1 n, -1, 1 to the power n, and is definable with empty interior. Then the set of concern here, xqt, for any t, if you consider a set of rational tuples in X of height at most t, you can cover this set by k into t to the power epsilon many hypersurfaces of bounded degree. And this k and d depend on epsilon and the set X. Okay, and I mean it will be critical, as we'll see, that we can have these hypersurfaces to be of degree which is bounded. The hypersurface is, of course, the zero set of multivariate polynomial equation in n variables in Rn. Okay, and all right. And so again, to set some notation, k is always a positive real number, and d is a natural number throughout the talk. All right. So I'll sort of restate the result when I apply it again, but really, I mean, it's just the set of concern for us. We can just cover it by so many hypersurfaces, and this number of hypersurfaces is sort of compatible with the final bound we're looking for. It does not exceed it anyway, so it will work out. All right. Now I want to give a very rough sketch of the proof of the Pila-Wilkie theorem modulo these ingredients or this black box that I just stated. All right. So I want to prove so X in Rn is definable with respect to this fixed orbital expansion of the real field R tilde, and I want to show that the number of rational tuples of height at most t in the transcendental part of X is bounded above by c into t to the power epsilon. All right, and for every epsilon I need to find such a c. That's my task for now. All right, I have a couple of images coming up, so let's just see a couple of cases and sort of try to understand how our proof might proceed. All right, so let's just fix some epsilon and some t for now, and let's assume that x is inside this bounded box. All right. So this red part, this red curve is x. Let's say we have a curve in R2, denoted by this red curve, and these yellow lines are supposed to be hypersurfaces in R2, right? So these are just algebraic curves, and so they can intersect x in one point, more than one point, or sort of an infinite set, like the middle curve intersects, right? X. All right. So if there's an infinite intersection, like for the middle curve here, well, you just project it down. Just forget the second coordinate, and you get an interval in R, right? And the part that is both blue and red, you see, because it's also blue, it is by cell decomposition. This is given by sort of a semi-algebraic map, right? And on this interval, and so must be semi-algebraic, and so is this part of the algebraic part of X, and so it doesn't matter, right? And so if there's an infinite intersection, it sort of doesn't matter, and hopefully I've been able to convince you of that. And then only finite intersections matter, and so well, any intersection of a hypersurface with X can only contribute at most finitely many points to this set of concern, xqt, right? And well, I mean, because the degree of these hypersurfaces can be bounded, they belong to a semi-algebraic family, and then we have a bounded number of connected components of this family, or the number of cells in a decomposition of this family. and so on. So that is that constant m. And k into the power epsilon is the number of these blue lines or curves I might need to use. And so this, for the one-dimensional case, we sort of have this. I hope I will be able to convince you that this is, anyway, this was our intuition, and now I'll give a nice detailed thing later. But you can, it's good to have this example in mind while we go to the sketch in a few minutes. Okay, and okay, one more picture. And so say we have in R3 a plane, which is given by this yellow rectangle here. And this red line is again some set in the plane, right? And also this pink line is also, let's say, some set. And we again our intuition is that, okay, I mean, this hyperplane, it's a cell, and I mean you break it up into cells, and locally you just project down every cell. These cells come with nice projection maps, right? Which are homomorphisms onto the range and so on. And so you just project them down. And I mean, surely, I mean, if you just tilting things, the geometry should remain the same, and rational points should go to rational points and things like that, and it should work out. But again, we'll soon see more precise details. But this was really the intuition of the proof the Pila-Wilkie had in mind as well, where I mean, you just take a hypersurface. If there is a top, if there's an intersection which is the same dimension as that of the hypersurface, well, you then prove that this must belong to the algebraic part of X. And if there is something of lower dimension, you just push it down through induction. And well, we just simply push everything down together using this simple projection maps that you get with cells automatically with minimality. And okay, for them, they also do some analytic argument with manifolds and so on, but we simply avoid that, which is simple projection maps, as we'll soon see. Okay, so let's now get just to sort of these two images hopefully motivate the following lemma, where it was really modulo this, everything reduces to simple bookkeeping in this part of the proof, at least. Okay, so suppose we have a semi-algebraic set X. You can have in mind that S is this hyperplane, this blue hyperplane here, and X can be this red thing. So and suppose we have this map F, which maps S to a Euclidean space, so that F is semi-algebraic and injective. I mean, we'll apply these only to projections, and they're semi-algebraic, and if for certain domains they're injective. And suppose F maps X homomorphically onto this image, which we set to be Y. Then the algebraic part goes to the algebraic part, and the transcendental part goes to the transcendental part. So we can shift all the geometry upstairs to a lower dimension, and then we just work on induction. Okay. So let us also quickly go to the proof of this lemma. Well, okay. So if you pick a connected semi-algebraic curve inside X, then well, I mean, F is semi-algebraic if you map it and injective, and if you map into Y, you also get a connected semi-algebraic curve. So no problems proving this inclusion. For the reverse inclusion, let's consider an semi-algebraic connected curve inside Y. Then this map, then F is injective on Y. F is a homomorphism on X, and so F inverse is in fact a map, and restricted to this curve C is a semi-algebraic homomorphism. So F inverse C is semi-algebraic, and because this is like a topological homomorphism, the image is also connected, and so F inverse C is also part of the algebraic part of X. So really, I mean, for projections, essentially what we want is the projections and so on, restricted to cells. This geometry transfers down very well, and then we are really in business. Okay, so now let me get to the sketch. All right, again, let me state the Pila-Wilkie theorem. I start with the X, definable in this fixed O'Neill expansion of real field R tilde. And I want to look at the number of rational tuples of height at most T on the transcendental part of X. Okay, fix an X. And well, let's say n is equal to 1. So X is X is in a subset of R, right? So I mean, R tilde is O minimal. So X is a union of finitely many points and intervals, right? Intervals are part of the algebraic part of X. And well, points, I mean, by cell decomposition, there are only finitely many points, or by the O minimal assumption, rather, there are only finitely many points. So that's the base case is very easy. Now let's set up induction. Okay, and well, really, if you have an open subset inside X, you can just for any point just draw straight lines and so on, and have it occur on the straight lines are small enough. I mean, you see that any point in the interior is part of a semi-algebraic curve. So really, we can assume that X is empty interior because anything in the interior is taken away by the algebraic part of X anyway. And then there is it's standard to reduce to the case where X is also a subset of this box. In fact, you can use the lemma that we just saw to do this as well. All right, so now you see I'm sort of arranged X such that we can apply a black box to X. Okay, so this is sort of a restatement of the black box as well. So X is of empty interior inside this bounded box -1, 1 to the power n. And so we get that the number of rational tuples in X of height at most t can be covered by k into t to the power epsilon many hypersurfaces in Rn. And this family of hypersurfaces have bounded degree, let's say d, and the d and k belong on X and epsilon, but that's fine. All right. So we have our points of concern, and we have covered them by hypersurfaces, right? Okay. And so then I claim that it's enough to get the bound we're looking for X intersected with any of these hypersurfaces, right? Okay, I mean this is sort of easy to see because I mean they are k to the power t to the power epsilon many hypersurfaces. If we get the same quality of bound, it doesn't hurt us too much. And so yeah, I mean that's why it's important to get the number of hypersurfaces to be a number which is at most but does not disturb our final bound that we aim for. Okay, I mean, okay, we have to break up X into some pieces, finitely many pieces, but that's fine because this sort of impreciseness in fact works in our way. If anything, we're counting more points than necessary, given by this. If you look at this inequality at the bottom of the page. All right, but anyway, hopefully I've been able to convince you that it's enough to look at instead of X to look at rational tuples of height at most t on a transcendental part of X intersection H instead of the transcendental part of X. Okay, and assume for purposes of simplicity of exposition that H is in fact a cell. I mean, H can always be broken down into finitely many cells, and it's routine to complete the proof even in that case. But let's just assume that H is a cell, and well, necessarily it's a hypersurface, and its dimension is one lower than the ambient dimension, right? And we'll use this fact to sort of appeal to induction. Okay. And so this is the map we'll want to apply our lemma to. So H is a cell, say, and let's now rename it to C. And these cells come with natural projections, right? Where you just forget some of the coordinates, forget some of the relevant coordinates, and you get a homomorphism of the cell onto an open subset of another Euclidean space, right? And this Euclidean space must have dimension. I mean, of course, the same dimension as the cell we were working with, and so same dimension M, and so these projections are homomorphisms, and so now we are really in business to apply our lemma here. Also, one more thing. I mean, again, this sort of error that we introduced, we are forgetting some coordinates, but if anything, we are counting more points again. Because if you're in a rational tuple of height at most t on top, you're also a rational tuple of height at most t down below. All right. So we set Y to be the image of X intersection C, and now Y lies in the Euclidean space of dimension lesser than n. So we can apply an inductive assumption. And so the number of rational tuples on the transcendental part of Y is bounded above by b into t power epsilon, where this some constant b is independent of t. So now we apply our lemma to X and Y. So X, P satisfy P in the role of F, and X and Y in the role of X and Y in the lemma. So P is a projection map. It's semi-algebraic. It's injective on C, and it's homomorphism on C. Never mind on X. And so we sort of lift. We know that algebraic part of X goes to algebraic part of Y, and the algebraic part and the transcendental part likewise. And so we can pull the bounds on Y, the transcendental part of Y up, and the number of rational tuples of height at most 3 on the transcendental part of X intersection H is now also bounded above by b into t power epsilon. Okay, and well, I mean, this b, I mean, so my claim was that that the constant C1 that we get in this displaced equation must not depend on H, and for that we sort of have to do this proof for definable families, really. And so we must intersect H with the definable family of hypersurfaces of degree less than or equal to d, and then run the whole induction with definable families and so on. And so that is what Pila-Wilkie had to do as well. But this is now model this idea just as something that one needs to work out. All right. And so let me just now state some of the theorems we prove or reprove in our note. All right. And so as I just said, I mean, the proof motivates a definable family version. And so let X be a definable family of sets in an omnial expansion of the real field. And then you have that for any epsilon, there is a C that works for all T and for all S in the parameterizing set for the definable family. And we have that the number of rational tuples of height at most T on XS, transcendental part of XS, is bounded above by C into T power epsilon. All right. And then, in fact, Pila-Wilkie proved this second version of the theorem here, which is somewhat stronger in the sense that instead of taking out the algebraic part of X, you take out a definable subset, which is a subset of X. And as we saw an example before, I mean, this algebraic part of X might not be definable. So this is strictly stronger, and you get the same quality of bound. But now in this case, you sort of take out a definable part instead of taking out all the semi-algebraic curves inside X. And so we sort of reprove this as well. And okay, and in the images and in the proof, we saw that really what we want to deal with is sets of the form Z intersection H, where Z is definable and H is a hypersurface. And when you sort of have that this Z intersection H equals the dimension of H, that is the case really where Pila-Wilkie had to use this analytic argument and so on, and that is what we have to handle as well. And so really what one has to prove that this if the definable set inside a semi-algebraic set and dimensions match, then the definable set is in fact a union of semi-algebraic curves. All right, and so now we define to capture this phenomena, we define a block of dimension d in Rn to be an open connected subset of a semi-algebraic set A, such that the semi-algebraic subset A has sort of uniform local dimension. I mean, there are different ways to skin the cat here, but and all of them should work out, but we found this the simplest to work with. And so I mean, notice this is it is clear that a block is always part of the algebraic part of the ambient set. Okay, contrast this with Pila's version of the block, which appears in a later paper, where a block of dimension D is again definable, connected, and open, subset of a semi-algebraic set, but now the semi-algebraic set has to be a C1 submanifold of dimension D. And so this sort of analytic argument is something that we are completely able to avoid in this part of the proof for the results in the previous page, and also so the result, this block family version that I now present to you. And so Pila proved this block family version in this next paper, which is really critical to obtain these extensions of the Pila-Wilkie theorem, where instead of counting rational tuples on definable sets, you count points from Q vector spaces of finite dimension or algebraic points and so on, of bounded degree and so on. So you really need this sort of, in fact, this theorem is really a corollary of the proof of the theorem, Pila-Wilkie theorem, but you really need this more refinement to get these generalizations that Pila got in his subsequent paper. Okay, yeah. So this is, I think I sort of ended early, but this is all I had to say.
We certainly have time for questions.
Yes, yeah.
So I have one question that
yes,
probably the answer is no, but in this points counting business, this Pila-Wilkie business, is there any difference between polynomially bounded structures and non-polynomially bounded structures?
Well, I mean, yeah, I mean, not for this proof, but yeah, I mean, there are some refinements where people look at making this constant C effective, and I don't, yeah, not sure. I mean, so I mean, the answer to your question is that I don't know, but they look at some functions that satisfy some nice differential equations and so on. But difference between polynomially bounded and non-polynomial, I don't know. Yeah.
Thank you.
Yeah. Maybe someone else does in the audience. Yeah, I've never seen that being a dividing line in this context. Yeah.
I mean, the big difference is if you define arbitrary analytic functions, or if you don't, because like if you're an expansion of Rn, you know you can't prove the theorem.
Sorry, you cut off at the end, Gareth. Yeah.
So well, a dividing line is if you're an expansion of Rn, then you have these unpleasant functions which show that the theorem is essentially optimal. Mm-hmm. Whereas if you're not an expansion of Rn, you can sometimes hope to do better. That's
yes. I mean, yeah. I mean, some directions one goes in is making the C effective. I mean, restricting the class of function sets that you consider, as Gareth alluded to. You can look at Wilkie's conjecture and so on. And but in general, I must say, I mean, this I've not seen in this more general setting where you consider sets that are definable in a general Omelin expansion of the real field, that C being effective. Yeah, perhaps Gareth can tell us how fruitful that endeavor can be.
In an arbitrary minimal structure.
Yeah.
I don't think it makes sense then.
Mm-hmm. Yeah. There's no bound on the number of connected components that these, cell decomposition and so on. So,
but it also effectivity has to be in terms of something.
Yes.
So if you don't have some kind of effective description of the structure, then
So in this proof, I mean, if you sort of want to dig into it, ineffectivity comes from this black box, where in fact proof of it requires this monotheoretic compactness argument, and there, sort of are completely lost. If that is a question I may answer.
Okay, any other questions for Neer? Okay, so thank you, Neer, again.
You.
So next week, the speaker will be Arish Shaviv from Princeton. He talks about Schwartz functions on definable and other domains. And at 11, maybe even earlier, I don't know, there will be a question session on actually things related to today's talk about Gareth's lectures. So Gareth will be there to answer questions, right? If I'm not mistaken.
Stop the recording.
Okay.